Hey everyone, and welcome. Today we are going to tackle one of the coolest, most fundamental challenges in all of psychology. How do we take the messy, subjective inner world of the human mind and use the clean, precise language of math to understand it? Let's jump right in. It really all boils down to this one question. I mean, think about it. How do you actually put a number on a feeling? How do you quantify an experience that, by its very nature, feels completely personal and, unmeasurable? This is the central puzzle we're going to try and solve today. And we make these kinds of judgments all the time, right? Without even thinking about it. We just know that red is way more similar to orange than it is to, say, green. We can hear a melody and recognize it's just a slight variation on another one. We're constantly weighing how similar a risk feels to a potential reward. But how much more similar? Can we actually create a map of these relationships? To answer that, psychologists realized they needed a completely new kind of ruler. Not one for measuring inches or kilograms, but for measuring our internal world. And this is where things get really clever. The official name for this toolbox is psychological scaling. And the whole idea here is basically one of translation. It's about taking all those subjective comparative judgments, things like, I like this one more than that one, or these two feel similar, and systematically turning them into a structured quantitative scale. It's about turning our gut feelings into actual data. And this isn't some newfangled idea. We're talking way back in 1927, when a psychologist named L.L. Thurstone laid the foundation for all of this with what he called his law of comparative judgment. He was one of the very first to figure out a really rigorous way to build a measurement scale just from asking people to compare pairs of things. He showed that, we actually can find a logical order inside all that subjective noise. Okay, so if we've got ourselves a ruler, what's the next logical step? Well, you build a map, of course. And this leads us to one of the most powerful and honestly elegant techniques for doing this, multidimensional scaling, or MDS for short. This is hands down the best way to understand what MDS does. Just imagine for a second you have no map of, say, Europe. None. But what you do have is a giant spreadsheet that lists the driving distance between every major city. Paris to Berlin, Berlin to Rome, Rome to Madrid, you get the idea. Now, using only that distance information, do you think you could draw an accurate map? The incredible answer is yes, absolutely. And that is precisely what MDS does, but for our psychological concepts instead of cities. So how does this magic actually work? Well, thanks to pioneers like Joseph Kruskal, we have a pretty clear process. First, you just collect the raw data. You ask people to rate how similar things are. Then a computer algorithm just kind of throws points that represent those items randomly onto a 2D space, like a blank map. And then, and this is the amazing part, the algorithm starts shifting those points around over and over, trying to minimize something called stress. Stress is just a fancy word for the mismatch between the distances on its map and the similarity ratings you gave it. It keeps tweaking until it finds the one perfect arrangement that best reflects what people told it. And what you get at the end of all that is a psychological map, a literal map of the mind. It's this incredible visual that shows us how we organize concepts inside our heads. Things we think are super similar, they're huddled close together on the map. Things we see as totally different, they're way far apart. It's a snapshot of our internal world. Okay, but having a map is one thing. Using it to navigate the world, that's a whole other ballgame. These psychological maps are pretty static, but our perception of the world is always in motion. It's an active process. So now let's look at how our brain doesn't just measure the world, it actively organizes it. And this is such a key idea to get your head around. Perception isn't passive. Your brain isn't just a camera, passively recording whatever comes in. No way. Your brain is an active construction worker. It's taking this chaotic flood of information from your senses, and it's structuring it, grouping it, and building a coherent reality out of it every single second of every single day. Now, psychologists usually break this organizational process down into two main flavors. You've got bottom-up processing, which is totally data-driven. You're building your perception from the ground up, starting with all the tiny little sensory features. Then you have top-down processing, which is concept-driven. This is where your expectations, your past experiences, and what you're paying attention to actively shape how you interpret all that incoming data. And in reality, of course, these two are constantly working together in a seamless dance. Let's make this real with an example. It's called auditory streaming. Imagine you hear a series of alternating high and low tones, something like beep, boop, beep, boop. Now, sometimes your brain hears that as one single kind of galloping rhythm, but other times you might hear two totally separate streams of sound, a high one and a low one. So why the difference? A pretty recent model suggests it's this awesome neural tug of war. You have fast connections in your brain linking tones that are close together, trying to group them. But you also have this slower, delayed process that actively pushes apart tones that are further away. And it's this constant push and pull that decides which reality you actually hear from the exact same sound. So we've journeyed from simple measurement all the way to this active, complex process of organization. For our last section, let's take a peek at how all these big ideas are fueling the absolute cutting edge of cognitive science right now, computational modeling. Today, researchers are building these incredibly sophisticated computer models to try and simulate all these mental processes, and there are a ton of different ways to do it. You've got things like attractor neural networks, which think of memories as stable patterns that the brain activity falls into. You have Bayesian models, which treat the brain like a little statistician, constantly updating its beliefs about the world based on incomplete or noisy data. And get this, some models are even borrowing principles from quantum theory to explain some of the really weird paradoxes of human judgment that classical models just can't handle. So, what's the big takeaway? Why does any of this matter? Well, the applications are absolutely huge. If we understand how we perceive and organize our world, we can build smarter, more human-like AI. We can get a handle on the cognitive biases that trip us up when we make important decisions. It gives clinicians new ways to investigate what might be different in perception for people with conditions like schizophrenia. And maybe most importantly, it helps neuroscientists build that crucial bridge between our abstract theories of the mind and the real physical wiring of the brain. Which leaves us with this final thought. From Thurston's simple comparisons almost a century ago to the mind-bendingly complex computer models of today, we have gotten so much better at creating these maps of the mind. And the ultimate question they force us to ask is a pretty profound one. If we get good enough at mapping these internal landscapes, does that mean we'll eventually be able to predict the paths we take through them? Definitely something to think about. Thanks so much for watching.